Hi and welcome to my workbench. Today I'm going to take a quick look at PRA 10.0 and go through the basic setup of the program and how to get you up and running as quick as possible once you get your gamma spectrometry kit opened and ready for action. So to do that demonstration today I'm going to use the GS-1100A, which is my entry-level gamma spectrometry kit, consisting of a GS-1100A, a GS-1515 sodium iodide detector. The kit comes with the manual and all the cables you need, but it's very much easier to see a demonstration than to read the manual, so let's do a quick one. We're going to hook the GS-1100 up to the sodium iodide detector with the BNC cable that comes with the kit, and this is a single wire detector, which means the cable not only provides the high voltage required for the detector, but it also sends the pulse back through the cable and gets decoupled in the GS-1100. So it's a very simple setup and works very well. To get a better result on the screen today, I'm going to use a very simple shield. I have a shield here that I built myself. It consists of a PVC pipe. It's actually a PVC plumbing pipe with a cap and a base, and it's lined inside with a smaller pipe, and the cavity in between is filled with lead pellets. So it's a moderate shield. It's not the perfect shield, but it works quite well. The GS-1100A connects to the USB port, and this connection is for power only. Just to get this one the right way around. And the audio connector plugs into the sound card. And the ideal voltage for the GS-1515 is 700 volts, and the GS-1100A has a toggle switch in 50 volt steps, so you can set it to 700 volts exactly. This particular model is designed with Zener diodes as a voltage stabilizer, which means it might take 10 to 15 minutes to warm up and stabilize completely. If you're after a solution and want faster stabilization, we have the GS-1100 Pro, which has a voltage stabilizer in it and outputs the correct voltage from the moment you switch it on. Alright, one more thing before we jump across to the computer and do the rest there is to find a source that we are going to use as our calibration source when we're setting up the system. So I have a little lead pig here with a few sources, and I might just choose sodium 22 today, as we're all getting a bit bored with cesium 137, and sodium 22 gives us actually nice peaks for calibration. So this is my little radioactive source. I place that here inside the shield, and we should be getting a spectrum on that when we get started. You can hear the pulses coming through the loudspeakers of the computer if I pass the signal through. So this crackling you can hear through the computer now is the analog signal coming from the GS-1100A, the raw signal coming through the speakers. And just so it doesn't drive us crazy, we'll turn the speakers off. And let's go to the screen. On the computer here now, and we have opened PRA, and the voltage versus time window is the main control window which comes up. So the first thing we do is to open those windows that we are interested in at the moment. Let's go into the view menu. We want to see the counting rate versus time. We want to see, we could take a look at the interval histogram, and we might look at the pulse height histogram, and the audio input. Let's just tidy up our window a little bit here. Right, now we need the settings and control window, so the data acquisition and analysis, we need this for our settings, and we also need to see the advanced pulse filter. The first thing we need to do is to check that we have our audio interface correctly set up. So let's have a quick look at that. We are using the built-in sound input, and it's set to 96 kilohertz, which is the maximum sample rate that my computer can handle. Setting it to a higher sample rate than your sound card is capable of has no advantages. It simply records 2 sets of data for every sample point, so it's just a waste of bandwidth. So set it to the highest your computer is capable of, and at 16 bits per sample, and we are using the left channel, which is the on your audio jack plug is the tip of the plug. As for the output, we're using the built-in output on the computer, so that's okay. Now let's look at the data acquisition and analysis window. At first it might look a little confusing, but it's actually quite simple. Sections of it we're not interested in at all. The height threshold, that's the lower limit discriminator on the old system. I usually set that to 0.3, which is enough to discriminate any noise coming from the sound card, and still enough to catch the smallest pulses that your detector is capable of. The tolerance threshold, which is this number over here, and keep in mind we're only looking at the left channel here at the moment. The tolerance threshold is a shape threshold. PRA uses a sample pulse shape which it measures each pulse against, and will count it if the shape is within the threshold of the sample pulse. So those thresholds are usually quite small, like in the order of 0.5, 0.7, somewhere along there. So when I set the threshold here to 5, it's a very generous threshold, and it will virtually count every pulse that comes through. This is not a problem because in PRA version 10.0 and above, we have what's called the advanced pulse filter, where we can filter the pulses based on the tolerance after the recording has been taken place. So in other words, we're recording everything raw, and we can filter it down and tighten up the spectrum after the recording. This is the main difference of PRA 10.0. So let's set that to 5, and the tolerance correction is set to 0. In this experiment we're not going to use the tolerance correction at all because it contributes very little benefit at this stage. Going down here, the next section down on the data acquisition and analysis is the acquisition time limits. This section here can be handy if you are doing 2 controlled experiments and you want to count the exact same number of seconds or the exact same number of pulses. So what will happen here is PRA will automatically stop as it reaches this number of seconds or pulses. So at the moment they've been set quite high, so that's fine. This section here, analyze data selection, we're not particularly going to worry about that at the moment. That just narrows down the area you're looking at. Counting rate versus time, that's just setting the bin size. Counting rate histogram, that's also something we're not particularly interested in at the moment. Interval histogram, this we will be looking at, but we won't change any settings here. We keep the bin size to the smallest bin size there is. The pulse width histogram we're not interested in. As we're using pulse shaping, or the shape tolerance method up here, all our pulses will fall into 1 or 2 bins anyway. Now the last section here is the pulse height histogram. And the first thing we want to look at there is the bin size. So 0.01, that's into 100, so that's 10,000 bins. So on the old system of gamma spectrometry, normally you'd operate with 1044 bins or something like that. And in this case you can have up to 10,000 bins by putting it to 0.01. Normally that's more than you need. 0.05 might be a more comfortable bin size. And we'll leave these other boxes unticked for the moment, and we'll come back to those later. This section at the bottom here is simply an area where you can type in a comment. That's for your own reference, and it saves along with the files, or you might write down what source you are checking there. So in this case we'll just put NA22, and you might want to put how many seconds you're doing. So we apply those settings, and we should be reasonably happy with that for the moment. We're going to untick the advanced filter at the moment and click apply, so we're going to come to this later. So the first thing we're going to do now is to acquire the pulse shape, and we do that in the action menu up here, and we do a start pulse shape acquisition. Now that will read in a number of pulses until you stop it, and it will take the mean value of the shape of those pulses. So it calculates on the fly, it normalizes and zeroizes the pulses and works out the value for the mean shape, and this value is what's used to filter the pulses later on. So let's go ahead and do that and come back in a minute. As you can see, when you're doing the pulse shape acquisition, PRA discriminates any very small pulses and any very large pulses. And this is to avoid the distorted pulses. We're mainly interested in well-formed pulses. And up here we can actually see the pulses as they come in, and we can see here that we have a positive pulse in this case. If we were seeing a negative pulse in this area, then we would have to come over here to the data acquisition and analysis and change the height threshold to -0.3, which is obvious because the pulse is throwing downwards and our threshold is then negative. We now stop the data acquisition after recording about 26,000 pulses, and what we're seeing on the window here now is the numbers that represent the pulse shape, the mean pulse shape of those 26,000 pulses. And we simply click OK, and PRA now has sampled that pulse shape. We can now go proceed and start the data acquisition. So here we go, we're now recording our spectrum, and we're using the shape tolerance method, which you can see has been ticked here, and it's discriminating now according to this tolerance threshold that we have set up here, which is 5. And as we can see, we immediately see the sodium-22 spectrum starting to form in this pulse height histogram window. This window up here is the interval histogram, and this is similar to a pulse height histogram in that it's got counts along the y-axis, but along the x-axis it's got the interval between pulses. So it forms this exponential decay curve. And this window up here, count rate versus time, is simply the counts per second. Now we can change the bin size here quite easily over here. So if you want to do counts per 10 seconds, we can change that here, and we then get the bin size for 10 seconds. So this can all be adjusted in real time. Has completed. This took about 15 minutes, and as you can see, we had set the number of pulses to collect to 1 million, and it's reached 1 million pulses, and PRA has automatically stopped. And as you can see here, we've collected quite a bit of data, and we have a reasonable spectrum down the bottom here. So let's look at these boxes individually here. The first one is the counting rate versus time. As we can see, we have a steady recording all the way along there. There was no fluctuation in the count rate, as we would expect, since we had a source in the shield for the whole period of time. The next window down here is the interval histogram. Now we're just going to have a quick look at that. It includes some information that we might be interested in. And in particular this part here where it measures the dead time. Now the dead time is the time which is not available for counting pulses. So whenever you're doing a recording with a sodium iodide detector or any radiation detector for that sake, there is a period of recovery, a period of the length of the pulse plus the time it takes the system to recover before it can count the next pulse. In this case it's 0.169 milliseconds or 169 microseconds. And essentially on this graph here, this is the area to the left of the bins, which is white, where there is essentially pulses missing, because we can imagine that this exponential curve continues to 0. But this area is missing because that's the recovery time of the system. Alright, now this recovery time will become smaller as your sample rate becomes bigger, but it will never become 0, because the actual sodium iodide detector and photomultiplier tube has a finite recovery time. But you can certainly minimize this area if counting pulses is your main objective. Faster sampling rate and possibly faster scintillators and faster PMTs will narrow this dead time area down. So that's all I'm going to say about the dead time for now. Okay, moving down here, we can now look at our pulse height histogram, which is the spectrum that we're interested in. Now, the source that we were recording was sodium-22, so we know what those peaks are. I'll come to that in a minute. So let's look at how we're going to analyze and calibrate this spectrum. The first thing I want to do is to see if I can improve the resolution and maybe see some more in this spectrum by using the advanced pulse filter. So in order to do that, I'm going to switch on the tick box that says use advanced filter, click apply, and I'm going to play with this number here. I'm going to make it arbitrarily small, try 0.1 as a tolerance threshold, and if I apply that, we can see that certainly we narrow down the spectrum. We got a better resolution on that main peak, but we did lose something over here on the X-ray peak to the left. So I think that setting is a little bit too high. We can try 0.5. Certainly that brought back some of the samples in the spectrum. We can try 0.8. And once again, I think that sharpened it up better. We didn't lose too much, and we still were able to sharpen up the resolution a bit. So we can leave it there at 0.8. I'm pretty happy with that. The next thing we're going to do is show the Gorshin correlation. Now this is a calculation based on the standard deviation, which plots in the Gorshin correlation to the peaks. And it's actually quite interesting because it can show us where there is a peak that we can't easily see with the naked eye. This spectrum here is very clear, but quite often we have spectra which are nowhere near as clear as this, and then it becomes very handy. So let's see if we can calibrate this spectrum, and to do that we're going to select a region of interest for each peak. The first peak we're interested in is this one here to the left, which is the X-rays emanating from sodium-22. I'm going to select the region of interest by placing my cursor and clicking within the region of interest and pressing the F key on the keyboard. This will auto-select an area which is twice the standard deviation. I'm going to do the same for the annihilation peak, and I'm going to do the same for the gamma peak of sodium-22. So now we have 3 peaks selected. We know that this one is 84 kilo electron volts. This is the annihilation peak between electrons and positrons, so that's 511 keV. And then we have the gamma peak from sodium-22, which is 1.274 mega electron volts. So let's open the calibration panel, energy calibration. And we are going to write down the energies in the energy column. First one is 84 keV, next one is 511, and the last one is going to be 1274. Right, so the first column is for the units in arbitrary units. So we click on the within the region of interest of the peak, and we read up on top here what the mean arbitrary unit is. In this case it's 2.525. So we're going to enter that up here, 2.525. And the standard deviation is 0.264. You can see that over here. Okay, we do the same for the next peak. The mean arbitrary units are 15.105. And the standard deviation is 0.637. And finally, we do the last one, which is the mean arbitrary units at 35.587. And the standard deviation is 1.018. And we're going to use the calibration mode of interpolate. This will essentially draw a straight line between the 3 photo peaks that we have applied. So we're going to click apply to that and close that window, and then we're going to tick the box that says use energy calibration on the data acquisition and analysis. We now see that this x-axis has recalibrated itself and should now be showing very close to the real values. 1274, yeah, 1273.988. This one here is now 510.98, and this one here is at 84. So there you go, there's our spectrum, all nicely calibrated. One thing we can do here, if we are not interested in the region to the right of this peak, we can now discriminate that here by reducing the height, for instance, to 50 arbitrary units. And there's our spectrum, pretty good result if I may say so. And the only other thing we might show here is how we can show this in logarithmic scale, simply by ticking there and applying there. And in some cases this will reveal peaks that you otherwise don't see. And here this also makes quite clear the Gaussian correlation. It's quite easy from the Gaussian correlation to pick the center of the peaks by clicking on them like this. Alright, that's pretty much it. So thanks for watching.